The correct answer is E.
Yeah.
Okay. So yes, you have centripetal acceleration towards the center. If you're moving at a constant speed, that would be it. But because you are speeding up, you also have what we call tangential acceleration. This is the speeding up, slowing down component of acceleration. Okay? So, acceleration. So this is a vector notation that just says you have direction. Okay? The definition of acceleration is sometimes in textbooks they'll put 3 equal signs because it's really like this is the definition of it. You are doing final velocity minus initial velocity over time. Okay. We learned that last year, and we just talked about speeding up, slowing down, or we talked about centripetal acceleration, and we've isolated those two. But now we're at the level you can combine them. So acceleration, the vector overall is equal to the vector sum of centripetal acceleration plus tangential acceleration. So this is the towards the center of the circle. And this is tangential. So tangent to the path, always going in the same direction. Well, this is your speeding up, slowing down. And the vector sum of those two, resultant, is acceleration overall. Okay. This is defined as the rate at which velocity is changing. Okay. Good with that? So kind of like it's really important, especially as we get into rotational acceleration. It's really important to make a distinction between are we talking tangential or are we talking centripetal? Usually when they say acceleration, they're talking about the broad category. If they want specifics, they'll say centripetal acceleration. Rarely do I see AP saying tangential acceleration, but you need to be aware that there's a distinction between the speeding up, slowing down, and then moving circular path. Good? Isn't it cool? It's how everything just comes together. Okay. So you've got a 3-dimensional free body diagram. Car going, so that's speeding up. So you have friction going in, gravity going down, normal force going up, and the friction force applied, or whatever, like technically it's friction force from the wheels on the road, enabling it to speed up tangentially. Okay, hold on. Okay, so what we will do is we will break this up. We will make our axes in such a way that one of those is always going towards the center of the circle. And then the other one is going tangent to the circle, which enables us to say the sum of the forces in this radial direction is equal to centripetal acceleration. They put sometimes different textbooks. One of the confusing things about college is different professors use different notations. Different textbooks use different notations. Like there was one class I was sitting in, it took me 3 weeks before, oh! That's like, I don't know what the variable was, like, he's using that for velocity. Like, are you kidding me? Like, I've been lost this whole time, and he's like, this thing's velocity. And I'm like, I didn't know what that was. Okay, so it's really important that you decipher the codes, okay? So some textbooks, instead of centripetal, they're gonna say radial acceleration. The nice thing with AP is they have a certain vernacular, like they use different vocab consistently. The frustration gets when you go to college and different professors use different vocab, different. I learned it back in the 60s in Soviet Union. And they're like, okay, like, you just go with it. Like, can you really write? So radial is the same thing as centripetal. It's going towards the center of the circle. Okay? And then in the other direction, tangentially, you get your normal mass times acceleration. Good with that? Okay. So, understanding how to set problems up. Put one of the axes in the direction of acceleration. And in this case, you have acceleration in both directions. So you've got a radial or a centripetal component, and then you've got a tangential component. Okay. Good with that? Okay. Just general idea here. Sorry, it's dying. This is overall acceleration. Okay. Good with that? Have a conversation.
I think the acceleration of the rock is greater than the moon because it has less mass.
Mass of the satellite cancels the matter just mass of the aperture accelerating towards gravity.
Which is constant.
But the same
I
size
hope.
changes acceleration. The mass
Oh,
of
yeah, I
the
can't just it's equal to.
we're done before mass of the satellite. I've been across the night feels like speed of pebble.
Yeah, I just learned people.
No.
Yeah.
We can get into one of those, just as long as they're going fast enough.
Accelerates fast. He's a crazy shot.
Okay, what do you say? Correct answer is the same. Okay. So with the moon, what's playing the role of centripetal force is gravity. Okay? And it's experiencing centripetal acceleration. We'll say this is moon, this is Earth, and that distance is r. Okay? This is the mass of the moon. It's the thing experiencing the centripetal acceleration. Okay? So that's the acceleration of the moon. It's just centripetal versus the rock. That's just free body diagram. It's just gravitational force going that way. So you have gravitational force is equal to your net force equal to mass times acceleration, you have the same expression, it's just this is tangential acceleration. Good with that? Okay, you're still changing, the rate at which velocity is changing is identical. It's just changing in different ways. Thumbs up when you have a guess. Have a conversation. Tell them why you think so.
Because there's no forces in our
Yeah, we're not, so it's like.
Well,
Keeping-
yeah, well, it is the section K, but gravity tangential.
There's nothing causing us to get
Yeah.
tangentially.
Yeah, at the bottom of that.
So as it goes like this. It's coming in.
Yeah.
Correct answer is?
C.
Correct answer is C. Okay, what forces are acting on it? Gravity and tension. Okay, and that force has to be equal, is equal to mass times acceleration. Okay, so in this case, we're gonna do centripetal. Be force of tension minus force of gravity. Okay, and so mass times centripetal acceleration towards the center of the circle. Good? Okay. And that force is always in the same direction as acceleration. Always. Not influence or be influenced yet. Thumbs up when you have a guess. Have a conversation and tell them why you think so.
There's a zero vector. There's a huh?
There's a zero vector.
So, of course, my brain is saying C. I'm thinking, because if we tilt the axes towards the center of the circle, there's a trig component to that gravity.
Are these all meant to be hard?
What?
Are all these problems meant to be hard?
Yes.
Yeah.
I know, right? These are the easy problems. I am so not doing that.
Great, so it's gotta be going in a circle, yeah. Yes, so this is going to be M-A-C, force tension minus M-C. I think it's gotta go down, right? It's gotta go down. I think gravity is tangential to the circle. I don't think so. I think it's the acceleration. Then where to go? No, they cancel.
I thought there was the maximum point. So I started falling back downwards.
These are fun questions. What do we say?
I say D.
I got some C's and D's.
Probably the first system.
It could be right. but-
Find someone you disagree with and convince them that you're right and they're wrong.
Awesome. So how about this?
Which one do you think the answer is? Did I disagree with you?
I don't think I'm tweaking that.
Oh, hi, Mr. Powell.
Get this right?
What?
Did they get this right?
We'll get there.
Some of them.
So therefore, there's nothing that you should know.
I feel like I'm right.
I think it's like, because
Direction.
This is the second conversation.
They knew the answer after the first conversation.
They did. It was alphabet soup.
Alphabets.
Because the text was one way.
So then the follow-up is like, find someone you disagree with, convince them that you're right and they're wrong.
The force So it's acceleration towards the center of the circle, if we tilt the axis is like this.
Wanted the,
And then gravity's gonna pull it down with the tangential, and so the result that we expect is gonna be D.
What do we say?
D.
Ah! I hear like this half of the room is D. This half of the room is C's. D. Okay.
answer's F.
All right. So I heard a lot of good parts. Here. I would orient the axis like that. Okay, free body diagram can be tension, gravity. Yes? Okay, so just for communication purposes, we'll call this, I'll call this X, positive X direction and positive Y direction. Okay, just, okay. It's good to declare what's positive. So we know that the sum of the forces in the Y direction typically would not be equal to 0, but okay, I'll carry this out here. So you'd have Ft minus, a lot of times they'll make this from the vertical. That's just the classic. Usually they don't do it from here. So that angle is theta. So the Ft let's see, parallel lines, alternating interior angles, there you go, okay. So that angle there, so you would do mg cosine theta is equal to that. But at the highest point, right, maximum height, the speed is what? 0. So this in this moment is equal to 0. Okay? Some of the forces in the X direction are also not equal to 0. And this is mg sine theta is equal to mass times acceleration. And that is that direction, tangent to.
Oh, so right. I got there.
So, Mr. Smiley, did you orient your axes that way because it was moving at that angle?
Good question. I oriented my axes that way just because I know from pendulums, it's good to put one of the axes radially. Right. It does make a difference. The hard part is you can't conclude, you can't like land on, it's hard to like land on this. If you make your axis look like this. That's difficult to conclude. You're out of that. Okay.
Right.
Do not influence or be influenced. You gotta guess. Have a conversation. Tell them why not? You came to that conclusion.
Show your axis.
Stop
Why do you think it's D? Or whatever answer you decided. So it's moving.
For centripetal, I think pushing inwards is force potential minus mg cosine. So you can add.
It seems like C's probably D.
Very good. So there's going to be.
So he's got centripetal acceleration going towards the center because it's moving in a circle.
I'd say.
Right? Yes, it swings.
But there's,
So then, got gravity, X direction.
Correct answer is?
C.
You got a C, you got a B.
That was smart, really.
B, C,
I'll take a C.
find someone you disagree with. B's and C's are on the table. That's not, they're wrong and you're right. Do not talk to someone who you agree with.
My bad.
Talk to people you disagree with.
I got it.
We just figured out that it wasn't, it's already downward, so it's gotta come up somehow.
Well, it's still going down.
Not as aggressively as the
What one
actual
did
last
you
one.
have?
So somehow it's kind of so that acceleration.
Yeah, but I guess he is in that direction. I could have looked at it. So like,
Okay, just for reference sake, A is going in the direction of the string. C is going tangent to the path. Is everybody okay? Like, and B is somewhere in between. Just so that we're like,
Oh, I screwed up. Crazy result effect.
Whoa. This is gonna be
What's going wrong here? Oh. See, we're just result effect.
It's on the same level.
And also, if we're
okay. Correct answer is?
B.
Correct answer is B.
finally.
Okay.
You did it.
So, doing that, okay, you do now have centripetal force, therefore centripetal acceleration, because it's moving. But you also have the x component of gravity that provides some tangential acceleration. You are speeding up. So the vector sum of both of those gives us something in between radially or centripetal and tangential. Good with that? Learn some stuff?
So far.
It's good? Okay. Okay. The weird thing about this problem is this is a rod. Not a string. Not a string.
Is it massless?
It is massless.
Okay, yeah.
Equation sheet. Come back to the equation sheet. Yes, all of the rotational stuff is on the equation sheet.
Let me give you a little bit of a hint here.
No.
Okay.
Okay? You're welcome.
So we're not there yet.
So that's why Gene's in there. Man, sometimes I just wish gravity would turn off.
Would make physics easier.
I'm going to space, no more gravity, no more air resistance. It'd be great if you could breathe. My dream is to drift so hard. What if I'm space shuttle?
Are we seeing that? Probably. Yeah, sorry. Bottom is so bad, it's zero.
we have a guess.
Well, we done it. So put itself out there.
That was conversation.
So we're looking at the top, right?
Yeah. So,
And the final kinetic energy is MgH. That potential, sorry, final potential of MgH. Yes, but
I said the initial position.
Oh, no. Oh, that's very bad.
E squared over R is equal to FG.
it's also, it's not more.
We don't need to worry why.
But I'm thinking, that doesn't matter.
That's not important.
How much energy is needed to get up to the top? Let's get up to the top. You need to get oh,
So
And then you
I'll
have
put
two
seven.
times that.
There's no
And
energy.
you're up to that. So then you
not
just.
potential energy.
So at the end, it's just MG.
So now I'm thinking it needs to drop down and then go back up. Am I going to do that? I said B, but I think it's C now.
Because in like a circle, like this,
And the fact that it needs to drop down,
that potential
it
energy.
needs to
at
drop
start
down,
is
then it needs to go back.
But since you want
But-
to here,
What'd you get?
Not
so
bad.
the two
Or
are
B or C, not A.
MG.
I like
Wait,
it.
it might be A.
I can't get a single answer on that one.
Oh,
so I don't know what's happening.
You get 2R minus R, you get MG.
Oh, because I guess it starts
Yeah.
R, so. Oh wait, if I assume that that's zero, then I could just say
Because
it's just MGR.
the initial position right here, right?
I did
The
too
circle,
much.
I'm just gonna say
the
A.
radius is
Yeah.
In case it has solid.
A
That's all.
works,
Because
because if
there's
you're
no
starting,
height.
because to start with,
But
you have
since the
kinetic
finals
energy,
on
you still have
You
potential
have that
energy, right?
plus.
So you're still
Oh,
up some,
sure.
and that's all
Okay.
contributing to potential energy by the time you're all the way to the top.
then it's just
And your
covering the
potential
whole
energy at the top is just twice what it is in that middle position, because you're twice as high. So if you subtract that, you get what your initial kinetic energy would be, and then you get MGR.
But if we just said the initial position is equal to 0 for the gravity, so it's like height is equal to 0, and it goes back up, it's still MGR.
Yeah,
So either
So-
way,
I know.
definitely not
This
MG2R.
part is,
I like MGR.
because you're solving for kinetics initial.
Correct answer is
A.
definitively.
Yes. 100%.
Correct answer is A. Okay. Is mechanical energy conserved in this scenario? Why? Okay, yes, there's no friction. But what's the condition, when is mechanical energy conserved? When there's no non-conservative forces doing work. Okay, are there non-conservative forces acting on this mass? Yes. From? We're gonna put Earth and the mass in the system. So it's been shoved. It has that initial velocity. Are there any non-conservative forces acting on the mass?
Centripetal force.
So rod is a non-conservative force exerting force on the mass. Because if it didn't, we could call that tension force or, yeah, we'll call it tension. Don't take this too far. Debating, I wanna say this. I'm gonna retract that, forget it. We'll call it tension force. And so so that's acting on it. It's a non-conservative force. But is it doing work? Because it is not doing work because it's perpendicular, acting perpendicular to the direction of motion. There's no component that is parallel to the way it's moving. Anytime you're moving in a circle, whatever is playing the role of centripetal force does no work. Because it is acting perpendicular to the direction of motion. Are we okay with that? Okay, whatever forces are contributing to centripetal force don't do work. Okay, so mechanical energy is conserved. So what we can do is we can say, so here's a point and here's a point, initial, final. We can make the lowest point we care about ground zero. It goes below that, yes, but I don't care. Okay? And so it has a certain, has kinetic energy initially, and at the end has gravitational potential because it stops. Okay? So all you need is mgh, which is R. H is R. Good with that? Okay? Good question. Think, do not influence or be influenced. Thumbs up when you have a guess. Have a conversation.
Yeah. Yeah. So.
It should be able to make it back to where it starts. What potential energy gets converted to negative,
that.
It'll lose
all
all
the
speed.
kinetic will get put back into
Yes.
potential. There's
But-
nothing to make sense.
It's got
Less than.
No non-conservative.
So it's got not well, it's got conservative, not conservative force. That doesn't actually work.
No, it's just gravity's a conservative force.
And gravity is, but the force use.
Yes, but
That doesn't work. Yeah, it doesn't work. So it's
No,
conservative.
remember what he said, see, like, how, like, keep going up and it's expanding.
No, velocity equals zero, but
It's at the top, you're
Going
going
to
to
things
zero,
like
and there's
this,
no
man.
acceleration except straight down. Your only acceleration.
Who said?
yeah. Yes.
Yes.
You know, like,
What do we say?
A.
Definitively?
Yes. Yes.
Okay, so let's say we cut the ramp right there. How high will it go? No. Let's say we cut the ramp right here. Where will it go? It will go up. How high will it go? How fast is it going at that? Zero at that height. If we cut it right here, it's gonna go this way. Will it reach this?
No.
Why not? How much kinetic energy do I have here?
Zero.
Zero. It's all in potential energy. Yes? here, it's gonna do this, right? Does it have kinetic energy at that point?
Yes.
Which way is it moving? At the highest point, vertically. Sorry, horizontally. Ugh. Yes? It still has kinetic energy. Therefore, it does not reach that height. Yes?
Yes.
Okay. Will it make this path? No. For the same reason, it's going to do this, and then it's going to be in projectile motion. You need to be moving right here. Have you ever been on a roller coaster that's like, okay? The only way that you make it is because the roller coaster is strapped to the track. If it was free fall, whoop. Does that make sense? You have to be, folks, to do a circle, you've got to have some speed. Not gonna make it. Is that, yes? Does that make sense? In order to make it, you gotta start somewhere up here. Because you still have kinetic energy here.
What if you jump when you're
Good? Okay, so, did I mislead you? Because what's the difference between this and that?
It was already moving.
Okay, that's true, but we could,
We know it stopped at the top of the last one because I had a rod. This one doesn't.
right. This one has a rod and holds it up. Have you ever been swinging? Have you ever tried to, like, I've always tried to get my little brother, like when I was like, I bet you we can get you over. Like, it doesn't work because like you pump and at some point the string goes slack and you go, right? But if you had a rod,
So what he's saying is.
you could get it to work.
So what he's saying.
I mean, you'd have to like duct tape them on the swing. I think Mark Rover did that with the rocket. Okay, but it had to be a rod. If it was a chain, it's gonna go slack. Good.